Okay, so then the plan for neurocognitive methods today is to first finish the G lecture so that you can start preparing for the exam, and then to start with the practical aspect of analyzing neuroimaging data using SBM, and we'll start with fMRI then today. Good. Could somebody please close the door? That would be awesome. So the last bit in terms of EEG is to talk about frequency-based analysis, and we did a little bit of that last time in terms of preparation. So we discussed that one can look at signals, and signals in this case meaning real valued signal. So in terms of EEG, the data from a single electrode. One can view this kind of data, so a sequence of real numbers over time in what is called the time domain, and that one can use the framework of Fourier analysis, or more specifically Fourier transforms, and even more specifically discrete Fourier transforms, and then even more specifically, for example, the fast Fourier transform algorithm, to transfer such a signal into the frequency domain, where instead of looking at what the signal has as a specific amplitude, one looks over an entire time period and asks what is the frequency content of the signal in the entire time window. And frequency, and this is what we discussed last time, is to be understood as the frequency of sine and cosine function, or you can always also think of sine function, the frequency with different phases, so different offsets. And we discussed that there are these generalized cosine functions, which one can, where one can actually define these frequencies, and that this is an interesting mathematical framework that we will discuss in the coming winter term, and that you are very much invited. But we will not talk about it now, but leave it at this intuition that there's a time domain signal, and there's its frequency representation. And based on that, the first thing to discuss, or one thing to discuss, are filters, because we haven't really discussed them in terms of pre-processing, and one can always interpret filters in the frequency domain, basically that they act in the frequency domain, and this is quite natural to talk about filters. So the idea of viewing filters in EEG or any kind of signal processing from the perspective of Fourier analysis or frequency domain is the following. So the idea is that here you have an unfiltered ERP, so data from a single electrode, and you have voltage over time. And then the idea of Fourier transform or Fourier analysis is, as we discussed previously, is to transform this into the frequency domain here, where you now on the x-axis have different frequency components, again referring to sine waves and how many cycles they do per degree, and if you sum all of them up to get this back. And what you can see here is that there's quite some frequency content in the low frequency on the low end of the frequency spectrum, but there's also this peak here at 60 Hertz. If you look at this, any idea what this peak here at 60 Hertz might refer to? If you look at this and then see this, any intuition? Well, there is this on top of this rather low frequency movement of the amplitude, and as we will see in a second, if we remove the 60 Hertz peak, then these this saw-like pattern here will go away. And this is exactly the kind of thinking you should get familiar with. So it's fairly straightforward actually to make these transitions between time domain and frequency domain also just intuitively, because if you see high frequency content, then you, for example here, then you might ask that this is, know that this is this. Yeah.
So what's on the y-axis?
Here? Yeah. Now this is just this is the time domain representation. So this is just the amplitude in terms of microvolt, for example. This is frequency content. This is the plot here. This is the same plot as just maybe that wasn't clear, as this plot. So what we've just seen was on the left was this, and on the right it was this. It was just not that clearly annotated, but of course you all are reading the luck book, so you could infer it. Because this is straight from the luck book. So this is signal amplitude, and this is frequency content. More specifically, I guess it's some normalized power, but we will see that in a second. So this would be now the transfer of the time domain signal into the frequency domain, and then a filter can be understood as doing some weighting in the frequency domain. In this case, applying this kind of weighting function, so leaving all low frequency parts through, or basically weighting them with 1, and weighting stuff that is more at the high frequency end, weighting them with almost 0, so basically attenuating these frequency contributions. So if you think about multiplying this in a point-by-point manner, multiplying the frequency domain representation of this and this filter response, as it's called, frequency response function of the filter, then because here the filter is very close to 0 and here you have a little bit, you will not see this anymore in the frequency representation of the signal, and then you can do the Fourier transform in the other direction, and what remains is this low frequency components, which refer to these kind of bumps, but what you don't see anymore is this saw-like pattern, which refers to the 60 Hertz peak. Yeah. So that's how one can think about filters and how they attenuate certain aspects of the frequency spectrum. Of course, it depends all on the frequency response function, so on this function, what actually happens. And to this end, it's clear that you can do two kind of things at least. So you can have high-pass filters which attenuate low frequencies and let high frequencies pass, hence high-pass filter. That was not what we've seen here. What we've seen here was a low-pass filter where high frequencies, and high then meaning, let's say, above 50 Hertz or something, are attenuated, and low frequencies are left to pass. So that's the definition of a low-pass filter. But you can, of course, do more. You can do bandpass filtering, where you attenuate both high and low frequencies and let a specific frequency band pass. So for example, you have a bandpass filter that attenuates everything below 20 Hertz and attenuates everything above 40 Hertz, and then the band that is left through is from 20 to 40 Hertz. It's something you can do. And you can also do the reverse, which is called notch filtering, where you only attenuate a narrow frequency band, but let everything else pass. So I think it's a nice exercise to draw the response functions of these filters. So basically the corresponding plots to this middle plot, so that you clarify for yourself how the response functions for these filters, so or the weight functions, if you want the weight functions, these kind of functions here, how they look for high, low bandpass and notch filters. All of these filters are, of course, applied in or can be applied in EEG data analysis, but they are applied everywhere. So if you think about just, well, you don't have that anymore. When I was young, it was a great moment in the life of a young teenager, male teenager, I guess, to have his first Stereoanlage. Nobody has Stereoanlagen these days anymore, but of course you can still adjust the frequency spectrum. Actually, I think you cannot really, I mean, on these streaming platforms or something on a computer, you only if you're on audiophile, you might have the opportunity to actually change the frequency component of what you are listening to. Otherwise, it's fairly standard. But of course, what I want to say is that in music, so in audio stuff, you use filters, of course, also a lot. Basically, you use filters everywhere where you have signals. And we're talking about EEG here, so we have filters as well. So what can they be used for? So high pass filtering, so letting basically filtering out low frequencies helps for removing slow frequency drift. So if for some reason on each of your epochs you have this kind of drift because maybe the reference electrode was drifting and then all your data was drifting, you can get rid of that, much like you can do that in fMRI data by using a high pass filter that removes these very low frequency components of the data. But of course, this has an effect, and this is what we also discussed previously. This has an effect on the ERPs that you will get. So this is an example from the Luck book where you see in the time domain an unfiltered ERP here in black, and so in the non-dashed line, and then cutoffs of varying frequencies for a high pass filter. So the small dashed line would be, or this fine dashing would be that you filter out everything below 0.1 hertz. So that's 10 repeats, 10 cycles per second. So hertz is the number of repeats per second. Or you filter everything out, for example, that is below 1 hertz. Yeah, everything with a repeat of 1 per second. And what you commonly observe is that you attenuate the ERP amplitude in the time domain because you remove low frequency contributions. And yeah, so this right plot shows if you use different kind of filter settings and you look for significance, that the probability of achieving significance, maybe for, I don't know, for this peak to be above something, changes. I think this is not really that important. What's more important is that you appreciate that if you change the filter setting, of your EEG data, you also change what you observe in your ERP. And the next plot I've shown you previously, because this is what we've done in this in the course previously. So here, this is the checkerboard data from the data that you also have for high contrast and low contrast. And here we had filter setting of 0.1 of 1 hertz and 2 hertz, and you can see that this has an effect. It's not completely aligned in terms of that it's always getting lower, so these effects can be more complex, but it has an effect. Let's see what we have here. Here it's more like what we've also seen in the Luck. So here, if we have the 0.1 hertz offset, so filter offset, so the black line, then this is the strongest response. If you increase the threshold for low pass filtering, then you decrease the effect that you observe. and it's just something that is good to know. Then the question is, what is the appropriate filter setting? And for this, you ask Bernhard Spitzer, because he's the one who knows what the appropriate filter is. I think there's some kind of consensus that it's definitely below 1 hertz, and then it's a little bit a question of whether you 0.1 or 0.5. That's then a little bit kind of a community feeling that this would be appropriate. There was also some discussion about this recently. It's always strange when these things pop up, but there was a filter discussion where they actually, because usually in a paper you will not show data that has been filtered at different cutoffs, and it's always it's something that everybody knows essentially that this has an effect, but it's never really explicitly discussed. And then at one point people discuss it explicitly, and it's kind of, oh, we have to watch our filters, and then it disappears again. But yeah, you should always know that, of course, pre-processing changes results. The more important thing is if you, from my perspective, if you, for example, look at the P100 effect here, and you want to compare the high and low coherence, you want to low coherence, that's what we have here. If you want to compare the high and low coherence, these were different electrodes. Sorry, I wasn't clear about that. The high coherence has the non-dashed line, and the low coherence has the dashed line, and you see that if you filter them the same way, which is natural because you would apply one filter setting to all of your data, not to only one condition, the finding that, for example, the P100 is larger than for the high coherence than for the low coherence, it remains intact irrespective of your filter settings. So then it doesn't really matter how you filter it if you're interested in these differences. Filters can not only be understood, especially in this case now low-pass filtering. Oh yeah, this is the step here. So that was high-pass filtering. We're now looking at the effect of low-pass filtering. Low-pass filtering can be understood as removal of high-frequency noise, as we have already seen in this 60 Hertz filter example. So you can, and this is how also filters are often implemented, you can view that as forming local averages for low-pass filters, so that if you have something like this, you actually compute an average of adjacent time samples, and by this computing here, for example, a 3-point running average or 7-point running average, you smooth essentially this out. So you can also understand low-pass filtering as smoothing in the time domain. So also smoothing in fMRI, for example, you can also interpret as filtering. You can actually interpret every data analysis as filtering, because if you relax a little bit the assumption that this is all about the frequency domain, because essentially, like I said in the very beginning of the statistical methods course, it's data reduction. You emphasize certain data features and you minimize other data features. In this case, for example, the high frequency noise. If you call that noise. But of course, you can also not call that noise and say this is the most meaningful signal in this consciousness, and you are interested in the high frequencies. Again, you can play around with that and use fairly different filter settings if you analyze data yourself. So the typical cutoff actually for a low-pass filter in EEG is 40 Hertz. So if you're doing ERP analysis, you let everything until 40 Hertz through, and the rest you call noise and filter out. So nobody would actually high-pass filter ERP data at 10 Hertz as we did here, but you can see that this also has quite a dramatic effect on the components. So this is clearly something, so the 10 Hertz low-pass filtering cutoff, nobody would do that. But if you do, just for the fun of it, then you see that you have quite some differences in effects. So that was high pass and low pass filtering. Notch filtering, fairly straightforward if one thinks that one just wants to remove a certain frequency component. For example, if one does not do low-pass filtering with a cutoff of 40 Hertz, but wants to look at the whole frequency range from 0 to, let's say, 100 Hertz, but still wants to get rid of line noise, then one can, of course, use a notch filter that is very centered and very focused on a given frequency. And in this case, if this is a pure 60 Hertz contribution, then using a notch filter can, of course, also remove that. Yeah. But of course, if you use a low-pass filter and filter out everything above 40 Hertz anyway, then there's not much need of having an additional notch filter. Although then purists would start talking about interactions between filters, and then it gets more interesting. But from a pragmatic viewpoint and looking at the time domain, there's hardly anything that can be found. When talking about filters, the important thing is actually how the frequency response of a filter looks, and one can characterize these functions, so how much they weigh certain frequencies in terms of two numbers. This is more kind of some additional knowledge. So one can talk about the half amplitude cutoff, so that's when the filter response has filtered out 50% of frequency content. So you see, so if you go down this way, you see that you are at a 50% attenuation, in this case at 30%, and in this case also at 30%. And then the question is how steep that is, and this is kind of the slope. This is a very common characterization of these kind of weighting function. If you ever seen psychometric functions, you can have the same or some different parameterization of these functions. It's not something very specific to filters. But yeah, so one can talk about the half amplitude cutoff, the frequency at which the amplitude is reduced to 50%, or the slope, the frequency amplitude decrease per frequency range, like you would always define a slope. And then you can measure these things, and then it gets, I don't know, and it seems to get more scientific, but on the other hand, it's also just how you measure it. You can measure it in decibel, which is a logarithmic scale, and you can define a frequency rate in octaves. I think that's the reason why I have this slide, is because there's quite a lot of this in the luck book to explain this a little bit, but then it's also not really that important. It's more important that you understand that if you use a low-pass filter, that high frequency components will be filtered out, and that essentially means, if you look in the time domain, that you remove this kind of sizzling at high frequencies. That's important, and it's important that you know, if you use a high-pass filter, that this can affect the size of your effect, because you also filter out frequency power in the time domain that relates to just the thing going up and down on a low frequency. Hence, if you use a high-pass filter and figure out low frequencies, it gets hot. And the important thing is that you don't think that filters are specific to EEG. The same thing happens in fMRI, it happens everywhere. And then the specific implementation of filters actually varies. So you can have filters that use this transfer to the Fourier domain and actually act there, or you can have filters that are implemented as kind of these averages. And then there's quite a lot more to learn about filter implementation, which I don't have in here because it's also not that interesting. Good, so this is what I wanted to say about filters from the perspective of frequency domain stuff. Any questions about filters at this point? No, good. So then the last topic, time frequency analysis, because everything that we've discussed so far in terms of EEG analysis and looking at results was actually in the time domain, and this is also the starting point. But then you might have realized that a lot of people also in cognitive neuroimaging, cognitive neuroscience, like to look at EEG data in the frequency domain, and there's nothing wrong with it. The funny thing, or one of the findings, if you look into the literature, is that you have frequency people and you have non-frequency people. So some people that do frequency stuff, they always do frequency stuff, and they do only frequency stuff, and you always wonder, do they also have, because in their paradigms they also would have ERPs, and then you wonder, what about their ERPs, and they don't report them. And then you have ERP people that then don't do frequency analysis, which is also fine. So you have these two communities, essentially in EEG, cognitive neuroscience, and as I said also previously, looking into the frequency domain, that's interesting, but the motivation is often not quite clear, because the neurobiological idea behind looking into the frequency domain is not always well motivated, and often it really feels more like we look into the frequency domain because we want to find differences between conditions, and maybe we find differences between conditions, and then we find some in the frequency domain, and then we are happy and we can publish something. That's, I don't know. If there would be more computational modeling of time frequency stuff, then I think I would be more interested in that. But so far it's mainly looking at or finding differences. So what is the basic motivation? And this is of course true, but it's always not, also if you look into papers, it's not necessarily clear that the main motivation was actually to account for that, because this is not then looked at, it's just transferred to the frequency domain. The main motivation is that, as I previously also discussed, is that if you look into the time domain, you might have a latency jitter. So you might have perfectly well-defined signals as shown here over given trials, but because they have a shift in terms of the latency, or if you use the frequency lingo in terms of their phase, if you compute the average, on average you don't get much of a signal. Yeah? So essentially this means that if you do time domain averages, you might cancel out interesting aspects of the data. This is of course a good motivation for time frequency analysis. However, I rarely see in any papers that they actually show that, well, we got all this cancellation and now we needed to do time frequency analysis. They just do time frequency analysis. But of course, a good motivation for time frequency analysis is to do some aggregation over trials that gets rid of signal cancellation. What then is a definition of time frequency analysis? Because definitions are always good. So time frequency analysis is the study of event-related oscillations. So you're still thinking in the event-related paradigm. So there is some experimental paradigm. You know when something happens, for example, a stimulus onset or a motor response. So there is an event, and it's the study of event-related oscillations by means of an EEG time domain signal decomposition into frequency-specific magnitude and phase information, and the characterization of their changes over peristimulus time. So one thing is frequency-specific magnitude and phase, and the other thing is their change over over peristimulus time. So you don't only want to show the frequency power, but how it changes over time. But then more specifically, actually, time frequency analysis refers to a dynamic collection of many different mathematical measures that capture different aspects of magnitude and phase relationships of EEG activity. I would go as far as saying that every lab that does time frequency analysis uses their own idiosyncratic method for doing time frequency analysis, and what really annoys me is that they never explain really what kind of method they use. It's horrible. There are some good papers that review different ways to do time frequency analysis, but usually in these papers that people use, especially if they use some summary measures. So if they just do a time frequency analysis and say, okay, we use kind of wavelets or we use windowed Fourier analysis, it's clear. But then they start to compute certain numbers on these things and usually just reference some paper which might not really also not explain what is going on. Anyway, I'm sometimes a little bit frustrated with the time frequency stuff that I get to review, because it seems to especially nice to not really explain what you did, but then find some results. Anyway, it's the basics, most basic time frequency analysis that you can do is actually a moving window Fourier analysis. So we've seen Fourier analysis here, and now here the idea was that you have a signal over time and you do one frequency component, but of course you can do that in windows. So instead of using a single time window, you can of course use a shifting time window to do your analysis. So if you would do a frequency decomposition in this time window, then you get a frequency spectrum for this time window, then you shift your time window a little bit, and then you get a frequency spectrum for this time window. And if you do that repeatedly, then you get what's called the time frequency spectrum. So you get time-specific measures of magnitude and phase over a range of frequencies. The important thing is that the way you do that is can differ. So we discussed last time a little bit that you can also use wavelets for that purpose. But the end result is always the same. You have plots, and before I do these specific things, also because we have to leave the room in a second, what you get in the end, and then later in the other room I will explain what these things are. What you get in the end are these peristimulus 2D plots, where on the x-axis you have time, and on the y-axis you have frequency power. So if you think again of the basic Fourier analysis, there you don't have time and you just plot frequency power for an entire time period. Now you have to imagine that you use this frequency power for a time period, and you tilt it by 90 degrees, and you color code the power for a slice here, and then you look at the next time window like it was shown. Oops. It is as it was shown here. Yeah. So you basically do your Fourier analysis time specific, and then you plot the frequency spectrum for each time point. So let's take not a break now. Let's just move to the other room, because people will want to come in, and then continue with these questions. And this basically we just go over. We don't take a break. Okay? Finish this. So there were a couple of questions.
Yeah, I just wanted to ask what is this power event?
Oh yeah, we'll talk about this.
Yeah. And my question was if the sliding window, if it's overlapping with, if it's
Yeah, these are all kind of methodological details. In principle, yes, it's overlapping with itself, and then takes a local average. But there are many different ways to exactly do that. And then also you have the question of course, at one point you don't have a signal at all. So because if you have a sliding window and it's centered somewhere and you center it on the beginning of your signal, then on the left hand side, for example, you don't have data, and then you need to do something, and then you use this zero tapering, for example, that you put zeros there or not. And then, yeah, so there are a lot of methodological details that I don't discuss here. Yeah, so the thing is in terms of power and what you get from that. So the whole thing usually happens in the complex number space, which again, as I'm not doing the math right now, it's a little bit impossible to understand. But as you get these complex numbers out of the Fourier transform, you get essentially for each frequency some measure of its amplitude and some measure of its phase. And what is plotted in these graphs is actually spectral power. So this, so with respect to the graphs that I've just shown you, what you see on these graphs is power which doesn't have any phase information anymore. So you basically compute the square of a complex number, which then removes the complex part and just shows you power. So the spectral power that is usually shown is the square of the magnitude measure of a frequency, and you shouldn't at all try to understand it from a perspective of power or energy or something like this in physics. There's no sense in that. It's easiest to understand this, or the most straightforward and also correct way to understand this is just the magnitude of a given frequency component in your signal. So that's spectral power that people like to show. Total spectral power averaged. This is now important. So first we have this time frequency spectrum where we have time-specific measures of magnitude and phase. Then you can compute the spectral power, where you basically get rid of the phase information and just have the magnitude information. This you can plot. That's fine. And then, and this is important, what is defined here on the slide is that there are three different things that you can essentially do with it, and especially the difference between evoked and induced spectral power is quite important, because you always, if you look at the results of some papers, you should always check do they mean evoked power, do they mean induced power, and you will also hear both these terms in talks on EEG time frequency analysis. So what are these? They are actually all defined in terms of how the analysis is done. So there is not something inherent in the brain that is induced or that is evoked, or that somehow the paradigm determines whether you induce something or you evoke something, which I think the terms sound a little bit like, that you somehow this is an experimental manipulation. It's not at all. It just refers to how the analysis is done. So what are the specifics? First of all, you can compute something called total spectral power. For each trial, you compute, so each trial of the experiment, you compute the spectral power and use these squared magnitude values for each time frequency data point and average these over trials. So you should think in kind of a 3D matrix, or a 3D array in MATLAB, where each page in this array refers to the spectral power, time and power on its two axes, and then you have trials of a given condition. And you can average over them, and then you have total spectral power. Now, you can do things differently. First, you can compute something that is called evoked spectral power. This refers to the fact that you do a spectral decomposition in terms of time frequency analysis of a time domain average. This means you first, in the time domain, for a single electrode, compute the ERP, and then you do a Fourier transform of that. Yeah. Of course, in this case, because you computed the ERP, and the ERP, if you think about from the logic of how this whole thing was introduced, the ERP, if they are non-phase locked, or if there are things that jitter over time, cancels out, then in the evoked spectral power you only have what is called or referred to as phased log frequencies. So because you have you only see phased logged power because only things that were actually in line temporarily over trials is still represented there. And then you have induced spectral power, which works as follows. So you do the time frequency decomposition on a single trial, and by this get a single trial time frequency decomposition. And then you remove, ideally, from each single trial the evoked power to get the single trial based power spectrum, and then average this. Yeah, it's actually straightforward. I wonder why people are always so confused also when I do the oral exam. It's really straightforward. So this is an example. So here you have single trials, and here you have the time domain signal. Yeah? And the idea is that you have some phase log activity here. So this is the phase log activity, and you have some random phase activity. And now if you have these 4 trials and you average them for an ERP, standard ERP analysis, single electrode, amplitude over time, if you average these 4, because they are in phase over trials, you see them in the average. Here the idea is that things are not in phase, which you can see here quite clearly. So here you have an up in the EEG trace, here you have a down in the EEG trace roughly at the same time. If you average them together, you don't get anything out. So this would be random phase activity, and here then in the ERP you still see a little bit, but you hardly see anything. And then you can do the following, and in this case looking at induced power almost. So here you do the time frequency decomposition of this, and then of course you see that there is some low frequency, so this is 10 Hertz, low frequency power here at this point in time. This is just looking at it in time frequency space, and a little bit later, which refers to as this. Now, if you average these time frequency decompositions, which all have some power at this point in time, so which is, let's say, 600 milliseconds, if you average these together, then you obtain induced power. And there it then gets a little bit tricky, because some people call this induced power, and I would also be kind of happy to call this induced power, and some other people call it induced power only if you would subtract from the single trial the Fourier transform of this thing, which would mean that because here you have 10 Hertz activity in this time window, essentially, that you would subtract this, and only this thing that actually refers to the random phase activity would be visible in the average. This is there. Unfortunately, I cannot give a clear definition of what people mean by induced, because some people mean that you subtract the ERP time frequency power from the single trials, and some people don't mean that. So if somebody says, so here we have a great effect in induced power, you should always ask them how they did the analysis, because the terms itself, they give you some direction of what they might mean, but you cannot rely that everybody uses this term identically.
Why would you want to subtract the phase log activity?
Yeah, because you want to show that there is some activity that is actually happening in random phase, but it's important, and I think important in the sense that it happens on almost every trial. And the thing is, if you just show this, this is why if you just show this, then you always ask yourself, so what? So basically this here. So what is this now? Stuff that I would also see in the ERP. So is this just time domain activity, because this is what this first part is, or is that something that actually motivated you to do this whole time frequency analysis? Namely, if you only have this, because this you wouldn't see in a time domain average. This you see in a time domain average, it just looks a little bit different. So, as I'm not in that business, I think it's a lot harder actually to obtain some interesting effects that are actually based on random phase activity. So I think most people actually like to show this mixture of phase locked and random phase activity, because then at least there's something. And but then I don't see the additional benefit of doing a time frequency component if the most interesting thing is actually the stuff that you would also see in the average ERP waveform. Yeah, then just to show me the ERP waveform, then I know what's going on. And I have also a little bit more of a intuitive feeling that there's something going up and something going down. Here, you always have to make this additional step of saying, okay, there's not much happening in the high frequency, so this 10 hertz power here, okay, that would be something that goes up and down. But whether this is a meaningful, neurobiologically meaningful summary, I don't know. Yeah, what is this? Time frequency power. Okay. In panel A, the time frequency transformation was applied to the individual trials and the transformed data were then averaged. This plot therefore includes activity that was not phase-locked to stimulus onset as well as phase-locked activity. So this is a typical mixture plot. It's not the nicest mixture plot ever, because people usually would do this in color, then it doesn't look like some ghosts somewhere, but it would be colorful, and you would say, oh, that's neuroscience, time, frequency, and color. That must be meaningful. In panel B, the transformation was applied after the waveforms had been averaged together, and then here actually you see that this is this is purely evoked power. This and this is the same. So the interesting thing here would be the stuff, in this case here. This is, I think, from an original paper by Talon Bowley, who brought this whole thing up. The interesting thing would be to subtract this from this, and then you see something more than you would see in a classical ERP analysis. And it would be clear what you see.
And how often is this done?
Like that you subtract the evoked power. I don't know. I don't have clear numbers for that. I just have the feeling that whenever people show you time frequency data, that you have to ask them what they actually did, because you cannot rely on the fact that it's nothing bad. I mean, it's just important that you know what they did to understand what they're actually showing, and you cannot rely if somebody says induced that actually the evoked was subtracted from the single trial. This is what I found, and this is also what you found in reviews on discussing these kind of things. So the details are always important. Good, so summary. Motivation for time frequency analysis is to aggregate single trial oscillatory activity without cancellation. That's the basic motivation. But then in the end, maybe this is not always what is being shown. Fourier series and transform are basic signal processing tools that are used to this thing, but the whole Fourier analysis business is mathematically not that involved. I mean, it's just rests on calculus. You don't need probabilistic models to understand Fourier transform, but it needs some work, and you need to be familiar with different ways of representing frequency information and so on. And again, the invitation for the winter term. In cognitive neuroscience, mainly power is the fundamental measure that people use, where then phase information is discarded and you just look at the amplitude. And then the specific power type that people talk about, evoked power, induced power, or total power. is not due to Fourier analysis actually, and it's also not due to experimental paradigm. It's just determined by the order that you do averaging in the time or frequency domain. Yeah, that's just how it is. And one can go beyond frequency analysis using Fourier analysis by using wavelets, where you actually tailor the time window to the frequency that you're interested. Because, of course, if you have a very short time window, then looking at low frequency power is kind of tricky, because low frequencies are defined by the fact that they extend over longer time periods. And likewise, high frequency, you can actually make the time window quite small to make quite a very specific localization time. It goes into the Heisenberg uncertainty principle stuff. So you might find that in papers you actually see wavelet analysis, and also in the labs that you might work in. Have you looked at a time frequency paper in any other course? Yeah?
In this case,
and on what topic? In the motor cortex. And what is the topic?
How motor cortex activity predicts responses.
Okay, so that's Adrian's work, essentially. But related work. Okay, so this is important, and then you should immediately ask, so what do we see there? Induced, evoked, how was it actually done? And is it clear from the paper? You read the paper? I know it's too much. Okay, so frequency analysis. We looked at time domain versus frequency, filters, time frequency analysis, and that's essentially it for the EEG course. So this is again everything that we talked about, and everything that, of course, the oral exam will touch upon. And we have a date for the oral exam, which is also good. And again, for the oral exam, just memorize everything that is on the slides. Then you are fine. Read the luck book in addition, because sometimes it will not be really clear what was on the slide. But again, like for the fMRI, I will randomly select 3 slides and ask you what's going on. And usually I will try to tap into things that make a little bit more of a coherent story. So for example, questions that I like to ask is, what is our basic biological model of what we see in the EEG? And then you can talk about all the things that you learned about this in terms of pyramidal cells and blah, blah. Or I like to ask, so in time frequency analysis, there are these notions of induced and evoked power. Can you please explain what these things are? Or what are the basic forms of source localization in terms of dipole modeling versus source reconstruction? Can you please explain what these things are? Or what is another good question? Had one eye. How does ICA for eye movement correction work on the intuitive level that we treated it in the course? So these kind of things where you can talk a little bit, not like what is on the y-axis of EEG plots, and then you say voltage, and then I say good, next question. So something where it's where you can show that you actually understood what we discussed. Yeah. Other questions? Or questions about the exam, I mean? Yeah?
Have you set it on time?
No, I would send that around. Is there something else on that day? You don't know. It will happen. I will send it around.
9 to noon, like last time?
Or rather not. Rather in the afternoon. But that's 5th of July, and it's still like 3 weeks or 4 weeks in the future. Good. Then we're done with EEG, and we take a break now until 10:30, and then I guess we do 1 hour of programming, and then we stop a little bit early because I have to go to see one of the vice presidents today to discuss important matters. But not for me, for the world. Not about my job. Don't get it. the wrong idea. Good. Then let's go on at 10:30.